All right, gives me great pleasure to be introducing our fantastic colleague, Dr. Ran Klein. He has his background, his PhD is in electrical engineering, and he's an imaging physicist at the Ottawa Hospital, Department of Nuclear Medicine, also an associate professor at the University of Ottawa, Department of Medicine, and an adjunct professor at Carleton University. So Ran is well known for his work on cardiac imaging, example being rubidium-82 PET imaging, with really translational work and his research resulting in commercially available software for image analysis, FlowQuant, which some of you might have heard of, and a range of activities, especially in quantitative imaging, computer-aided diagnosis, and AI. And today he will be talking to us about a toolbox that he and his team have been developing, the PET Lesion Synthesis Toolbox, an integrated research tool. So thank you very much, Ran, for accepting our invitation, and excited to be listening to you.
Thank you for that introduction, Arman. So there's a picture of me, with COVID, we can't do this in person. So at least if you are in Ottawa and you bump to me in the street, you'll recognize me. This is work that's been done over the past couple of years, and really something that, we're doing it because we're interested in doing it. We think it's fun and we really want to share it with other people. We're not looking to commercialize it in any way. We're looking to be as collaborative as possible. So if this is something that's of interest to you, reach out. We'll find a way to put this into your hands. So usually people leave this slide for the end, but I like to do this in the beginning. The work I'm going to be presenting today is by no means my own work. Hanif Juma is really the star here. He was a master's student working in my lab, and he's really put a lot of this together, but he too relied on the help of others. And then we do have some people at the Ottawa Hospital that are looking to apply this. So I really thank them for their enthusiasm and encouraging us to work on this. I do have a few disclosures. A couple of these are relevant to the slide, to the presentation. So a bit of background as to what it is that we're trying to do as a big picture. So we're talking about PET imaging, and in PET imaging, we're looking for lesions. So hotspots that pop up and they are maybe associated with disease, maybe not. And there's a series of steps that has to happen between getting the patient into the imaging suite in the first place until you have an image to look at. And this has the image you'll get in the end depends on every one of these steps. You can really influence the type of image you'll get at the end. And the end result is that we're dealing with in this presentation is, well, there's a lesion in the image, and can you detect it or can you not detect it? That's what we're asking. And so if you want to tease how to introduce a lesion and then look for its detectability, ideally we want to do that as early on as possible, maybe by creating a disease model where we put lesions into a mouse and then we look at imaging them. Or we could do it further downstream where we artificially insert images during lesions during imaging. So maybe like a hot source that you put next to your rat, or maybe into your rat. That has been done as well. You can have physical phantoms that you image. So there's no living animal. You create the phantom, you know everything about the phantom, and you can tease out what you can see and what not, but with the understanding that a phantom is limited. Typically the phantoms by design and by limitations, they don't vary all that much. They're very simple from a geometric point of view, so they don't necessarily really represent what our patient is going to look like in the end. Then you can do this all in silico, so you can create what's called a numerical phantom. And again, you can be a bit more elaborate here, but typically the phantoms are somewhat simple. Even when you look at something like the XCAT phantom, organs within the phantom have a uniform uptake. They're very geometric in shape. But in the end, when you look at can you detect or can you not detect a lesion, you'll always need to compare to a reference, and it's the readers that can also be the reference, right? So if you really want to see can you detect something in clinical images, well, then what you need to do is you need to get a body of these readers together, and they have to come to a consensus and generate a ground truth by which then you can evaluate other readers. And that has real limitations because then you can only look at lesions that are perceptible to the human eye, typically in a reliable, robust way. So if you really want to tease out the limits of the type of lesions you can see, having reference readers is really far from ideal. So we're looking at doing something a little bit different. We want to introduce synthetic lesions that we are well characterized into real patient images. And we start by taking patient images, defining where we want the lesion and what characteristics it has. And then we apply some sort of modeling of our imaging system in order to generate synthetic data of that lesion that is incorporated with the patient's data and then is processed through to generate an image that has the lesion embedded in it. The benefits of doing it this way is that we also know everything about the lesion. So we have a reference truth. And now when the viewer looks at the image with the synthetic lesion, we can compare their performance to that reference truth and say, not only did they detect that lesion, but maybe we can also create a metric, which I'll talk about in a bit more detail, that I call the limits of detection. So what are the characteristics of that lesion that define the limits of whether it's detectable or not? How small is it? How faint is it? And can we use these limits of detection as a parameter by which we can benchmark or compare the performance of different readers or different technologies? So basically, this is the scope of my work. My research program, it's everything that has to do post-image acquisition. And we, of course, include in it human readers, which we want to tease out their performance. So really, for the task of lesion detection, how well they can perform with these types of images. And then, of course, we also want to do that with machine observers, what's known as AI, typically. But in today's talk, I'm going to focus on how we take these lesions and generate them. So how we create these synthetic lesions. So we started off on building what we call the Lesion Synthesis Toolbox. It's not the most creative title, but it is descriptive. And its mission is to create well-characterized synthetic lesions in real patients, both in PET and in CT. Okay, so we're focusing on PET CT here, and we want the lesions in both ultimately. We wanted something that's simple to use, so you don't need to be a computer programmer in order to use it. We want physicians to be able to use it, medical students, even psychology students to be able to use this. So for that to happen, it needs to be well integrated. We want everything in one place. We don't want to start transferring files and data. That includes connecting to the modality so we can retrieve data in the first place, and then also be able to send data to an imaging platform, whether it's a clinical system or a proprietary viewing system. And so we want something that's easy to configure and can be accessed, and without the need for dedicated hardware. So we didn't want somebody to have to go and buy a computer cluster or anything like that, just a desktop or even a laptop might do. So this is a very busy diagram, I realize that, but it basically describes the process for synthesizing lesions. It starts off, I hope you can see my pointer. Can somebody confirm? Yeah, okay, good. So we're starting off with CT and PET data that was acquired in clinic. PET is typically acquired in list mode and then is converted into sonograms or histograms before reconstructed. We take the PET and the CT images, we generate a fused display, define where we want our lesions, and what characteristics they have. And that defines our reference truth. Then we take that reference truth and we, along with the CT, which gives us our material map, we perform a simulation. It can be either analytical or in Monte Carlo. And then we can generate either the lesions in list mode space or in sonogram space. So the two alternative approaches. Whichever approach you take, then ultimately you have to combine the data of the synthetic lesion with the patient data and then reconstruct that image to get the final image. So that's the workflow that we're talking about. Now we played with two approaches. We played both with Monte Carlo and with analytical simulators. This is just kind of a comparison between the two. Monte Carlo simulations, as you may know, they do particle tracking. You can really model the physics very precisely. They'll generate data in list mode, which gives you the most flexibility with regards to reconstructing images. But they're very computationally expensive. They're complicated to use. While we have done it with SimSet, we did run into significant limitations. So we weren't able to get time of flight data, for example. So that wasn't really clinically applicable. And so we sought simpler avenues. Analytical methods are maybe not quite as accurate. They maybe don't model all of the physics to the same degree of precision, but they're much faster to run, easier to use. But they do have common challenges. So for both of them, you need to define the scanner geometry very precisely. You need to define the materials that the scanner is made of, and those data can be proprietary. Not all vendors are willing to disclose these information. Requires supporting many types of file formats, both from the vendor and from the simulation package. There can be a mismatch in the computing environment. So they may run on parts may run on Unix, other parts on Windows. And then when you develop all this, you need to perform extensive validation before you can proceed. So very cumbersome to make your own simulator. So even though we did that, we sought another approach, and we ended up focusing on analytical simulations. So this is kind of summarizes the pipeline. It's very simple. Basically says we're going to interface with our GE scanner. We're going to get data, de-identify it, define our lesions, generate lesion maps, perform a forward projection to get histograms, combine it with the patient histograms, and reconstruct the images. And so the workflow that I showed previously just gets a little bit simpler. And the solution that we came across for implementing all this was actually quite readily available through previous work from GE. So we reached out to the group there. They were willing to collaborate. And so the Lesion Synthesis Toolbox, as I'll present to you, emphasizes the GE solution. So the reconstruction toolbox was provided by GE, enabled us to do reconstructions offline, so we didn't have to go to the console to do them. These were validated to be numerically identical to the reconstructions that come off the clinical systems. They run on standard PC hardware in a MATLAB environment, which in our case worked out great because we're experienced MATLAB users. And it also had built into it already the capability of synthesizing lesions. So you could bring in synthetic data and it would be incorporated during image reconstruction using the same forward projector that is used during the iterative reconstruction algorithm. So what were the challenges when we received the package? Well, first of all, it only ran on Unix. All of our environment was in Windows. And so we worked with the GE in order to resolve that. You know, given that this is implemented in MATLAB, this shouldn't really be an inherent limitation. And so that was quite easily resolved. It only supported older versions of MATLAB, so we had to work with them on improving the compatibility with newer versions of MATLAB. And the documentation from GE was quite incomplete. So as we were going back and forth with them, we found some answers to our questions, and then we made sure that those were documented for later versions. So this was definitely collaborative research, and we're really grateful to GE for seeing us as a partner to improve this research product. Another limitation we recognized was that we had a research agreement with GE, so we could use the toolbox, but then once we want to disseminate this outside of our group, the GE structure at the time was that everybody needed to have a separate contract with them that explicitly said what work they were going to do using what tools. And we were very happy to engage with GE at just the right time when they were looking at establishing the researcher community. And basically what it did is it created a list of researchers, including your group, that once they joined in, we could freely share information between ourselves, including tools. And so that's really exciting. So if UBC wants to try out our toolbox, GE has given their blessings to disseminate without having to involve GE, which would greatly slow down the process. And lastly, the toolbox from GE is really designed for programmers, right? So it's in MATLAB, and you know, if we want novice people to be able to use it, that remains a hurdle, and that's part of the impetus for developing the Lesion Synthesis Toolbox. Okay, so this is what it looks like when you go to use it. So you launch the Lesion Synthesis Toolbox in one of three ways in our lab. You can either do it from within MATLAB, you just run the command. We can compile it and then deploy it as an executable application. We know we can do that in theory, we've never bothered to do it. A more attractive way is as a web application. So MATLAB can host a web app, and then you would access it, access the server from any computer that's on the network, just using a web browser. It enables for multiple people to use the toolbox simultaneously. And another benefit is that your computer, your personal computer, doesn't have to remain on and be busy doing the reconstruction. The server does all the work, and it can continue to do that even while you're away from it. The login is password protected, so you can control who has access. That is important because you may have data in here that is PHI sensitive. So I'll start off with some of the configurations, and I'll give you a hint as to some of the features that are in here. So in the configurations panel, you have some general configurations for connectivity to your Discovery scanner. So in our case, we only have one scanner, but you can configure as many scanners as you want, and select where you draw your data from. You can set up local server root directories. So where do you store the images that you reconstructed, and where do you, the queue for the images to be reconstructed, and where is the queue for images to be simulated. These are the way the reconstructions and the simulations are performed. They're performed as a background service. So you actually have a server that's running in the background, and it basically has directories where we dump data and they queue up for the server to do the reconstruction or simulation as in turn without prioritization. And of course, you can also configure user accounts. Next one is the projects, and each user can have multiple projects. And basically you say, here's stuff like, how do I want to label my data? How do I want my displays to look like? Which units, which color maps do I want to use? You can configure DICOM connectivity, so you can send your images to your PAC system or any other system that is DICOM compatible. You can create a library of reconstruction profiles. I'll show you a little bit more about that in a moment. And we also have push notifications. So that's one of the things we encountered a real need for as we were developing this. You queue up stuff for reconstruction or for simulation. It can take hours, and then it may fail, and you won't find out the next day. So we actually use a service called Push Bullet that'll push a notification to your phone to tell you if you successfully finished reconstructing or if an error was encountered. So I mentioned the reconstruction profile, so we can configure different reconstruction methods that we want to use. And then once we configure those profiles, we can use them over and over again without having to each time specify every parameter. And this includes the common things such as matrix size, reconstruction algorithm, number of iterations, post-reconstruction smoothing. Okay, so now you want to start using this tool. Everything's configured. Well, the first stage in the pipeline is what we call the discovery DR. So this is the interfacing the discovery scanner for data retrieval. And by doing so, you select a scanner from the pull-down menu. You can select a date range, and then you basically scan what's on the console, and you get a very familiar list of acquisitions and the series that they have that you want to pull. You're not seeing an artifact on your screen. This is a screen capture from our scanner, so I didn't want to include patient names. So that's why they're blurred out. Once you select your patients, the data that you want to download, you just hit the import button and everything is automatic. You select the pet data that you want to retrieve, and it will automatically retrieve CT data that is related to that scan. So you don't have to be explicit about that. Another nice feature is as you're retrieving the data, you can also anonymize it. We found that really useful because then you're anonymizing the CT and the histogram data right off the bat. And even after, then when you go to reconstruct or whatever, that data is already anonymized. You don't have any PHI that resides on your research machine. We use the FTP protocol in order to retrieve the data. So while the data retrieval works quite quickly, populating this is a little bit slow. We're talking about if you're scanning everything that's on your console, it may take as much as like 3 minutes maybe. But if you limit the date range, it's quite a bit faster. The next tab is image reconstruction. So as I said, this is equivalent to reconstructing on the console. Basically, you select the data that you want to reconstruct on the left-hand side. On the right-hand side, you select the reconstruction profile that you want to use, and you can preview the parameters for that. And then you queue the reconstruction. So as I mentioned, the reconstruction gets queued. So you're not stuck waiting for the reconstruction to be done before you can move on. You can select multiple scans, queue them up for reconstruction, and go grab your lunch. And when you come back, some of those reconstructions will be completed. The reason why we reconstruct in the toolbox and we don't use the reconstructions on the console is that we want to have the exact same reconstruction parameters for when we define a lesion and for when we synthesize it, so that when we sample the activity within the patient image, it's sampled using the same reconstruction parameters as will be produced in the final image. So that's why we did it this way. So onto the most interesting part, I think, and that's defining your lesions. So you start off by selecting the data that you want to use from your list of previously reconstructed images. So you can just preview the images and then select them. Then you go on to the next tab, where you basically have a user interface where with the pointer of your mouse, you specify where you want to introduce a lesion and then the parameters of that lesion. Now, this can really be developed over time for different types of lesions that one may envision. For now, we have what we thought was the basics, the bare basics in here. So what kind of parameters can you specify for your lesion? So obviously you can specify the shape. And right now we have two types of shape. We have what we call a sphere and what we call a blobby sphere. So a blobby sphere is kind of like an irregular shaped sphere. And that's still work in progress about what parameters exactly it should have. There's always a trade-off of having many parameters, and then it's very flexible, but it's also hard to use. So we're kind of toying with that idea. You can specify the intensity of your lesion, and there are 3 different modes you can do that. So you can either specify absolute units in becquerels per cc. You can do it relative to the background. So let's say you put a lesion in the liver, then you can say, I want this lesion to be twice as bright as the lesion as the liver. So it's a factor. Or you can do it relative to a reference region. So you can specify a reference region in the liver and then define a lesion in the lungs whose intensity will be relative to the liver. When you generate those lesions, there are 3 modes for how the intensity is specified. So it can, the default, which I think is what would be most interesting to most people, is, well, you specify what you want the final intensity to be. I want it to be twice the intensity of the liver. So you measure the liver and then you multiply that by 2. And then the final intensity in the reconstructed image will be twice the liver. You can also, so you can do that either as a uniform lesion, right? So if you have a big sphere, all the voxel values should be about the same. Or you can choose to maintain the texture. So what we do there is we keep the average intensity, what you specified, but we keep the variations in intensity values as in the patient. So for example, if you specify a lesion that's right on the interface of the diaphragm, okay, between the liver and the lung, then maybe half the lesion would be dark and the other half would be very, very bright. But on average, it would have the intensity that you specified. And then the last version is that it's just incremental. So you specify how much, what intensity you want, and that just gets added onto what is already in the patient's activity. You can also specify the CT Hounsfield units. So we can generate that lesion in the CT as well. And it's very simple at this point. It's basically just voxel substitution that we do in the CT, accounting for partial volume losses at the edges. And then, as mentioned previously, you also can specify the reconstruction parameters prior to setting the queue for simulation. The lesions that you specify are previewed. So you can kind of see that here on the image. There's a large lesion in the lung in purple. And so that's a preview of the image, the PET image intensity that you would see after synthesis. So, yeah, so I've already mentioned that just like the reconstruction, the simulations get queued. So in a very short amount of time, you can specify many simulations that you want to do. And even though the simulations can take hours, you're not stuck waiting for one simulation to finish before the next. So, an ideal way to do this is that Friday afternoon, you sit down for half an hour, you queue up a bunch of synthetic lesions. You show up on Monday and they're ready to go. So the last part that's in this tool is we have a local database of all the lesions that have been synthesized. And so you can pull up those images, you can view them within the toolbox, along with reference ROIs and lesion ROI parameters. So they're all listed here. And whenever you click on a lesion, it brings you to where it is in that image so that you can view it. It's nicely linked that way. So this is a good way to proof your work. And then finally, from here, you can also upload these images to your PAC system or whatever by DICOM send. You can copy the reference truth right out of the toolbox. It's just formatted text, so you can paste it into your favorite text browser. If you paste it into Excel, it even formats pretty nicely, so you can use it that way. And if you're a bit more savvy, there's also a mat file that's saved with the synthetic lesion that has all the information. So if you want to do like a perception study where you want to have a library that has images, let's say in DICOM format or in MATLAB format, along with the ground truth, well, those files are all there for you to take, aggregate, and use in your perception toolbox. This is just an example of a study, the way it appears on our Hermes system. So you can see here that basically there's the reconstructed MAC, so attenuation corrected image with an underscore LST, which is how I designate Lesion Synthesis Toolbox, and an associated CT. And then you can just view that in your clinical viewer. So just a few examples, here's a MIP with some of the synthetic lesions. If you don't know what to look for, then look in the mediastinum. That's where you'll see all of them in this example. And here's a few examples. So the crosshairs here are all centered on the synthetic lesions. And you can see that these all vary in size and intensity. So, how did we validate some of this? I won't get into all of it, but here's something very simple that, somebody can do on their own. You can create a very large lesion. So in this case, we created what we call the hot rod right through the center of a patient. And then you can sample that image after you reconstructed the original image from it, right? So we have the image with the rod, and we subtract for the original patient image. So what we expect to see is just the rod left over. So it gives you a feel for what the data looks like. It is noisy, and we expect it to be noisy. It's relatively low activity, and it does have noise artifacts that are introduced during the reconstruction and so on. When we sampled along the rods, one of the nice things we were able to show is that the bias is very low. There is a little bit of a bias. And also we deemed the variability or the noise to be quite acceptable. So we're kind of operating within the range of a bias of about 2% in the activity and a plus minus about 2% variation in the activity due to noise. We are looking into that bias. We want to fix that, but I think good enough that we can proceed. The hardware that we're running this on is just a standard Windows PC. So we do have a relatively high-end processor on it. We have a very basic GPU. Memory is important. So we have 16 gigabytes of RAM, which is sufficient to do. I think we did as many as 4 reconstructions simultaneously on the system. and maybe a distinction is that, again, we're using the reconstruction toolbox. So this is like an old version. So the way we did that is we had multiple instances of MATLAB running simultaneously, and we could do as many as 4 reconstructions simultaneously. My understanding is that the Duetto toolbox, which is put out by GE, is multi-threaded and will use resources out of the box more efficiently. So I haven't played with it yet. That's probably a month away from me implementing that. So I expect that there you would do it differently. You would just do 1 reconstruction at a time, but it would run a lot faster. With regards to how we configured our system, I think there's a lot of big files that get moved around. And so the way we configured our system is as such. So for our main hard drive, we have a small SSD, so it has our operating system and all our programs. For temporary storage, we have a slightly bigger SSD, and that gives us really good like read-write speeds. And then for permanent data storage, we just use traditional spinner hard drives, which are a lot cheaper to buy. So we have 2 12-terabyte hard drives, and they're mirrored. So if one of them croaks, hopefully we won't lose any data. So what are some of the applications? So I'll start off with something very, very simple that we did. So this was an abstract by one of the physicians in our group. And like I said, you know, she asked me to generate some lesions. I spent a Friday afternoon specifying them. This ran over the weekend. And by Monday, she was good to go. And basically what she asked was, when physicians evaluate lesion intensity visually, how well does it correlate with measuring SUV max values of those lesions using the Deauville scoring criteria? And so basically I generated for her something like 100+ lesions. I think it was 115 lesions in something like 15 different patients in various locations throughout the body. And then they went about doing their scoring. So my work was just generating the lesions, and from there they were off to the races. They put an abstract together very quickly for a conference, and were able to basically present that visual assessment correlated very well with SUV max measurements, but that there were some discrepancies between how readers interpret those images. A study that I was much more involved in is our first perception study. So here we just presented liver lesions to a series of viewers, and we basically asked them, find the lesion. For this, we used an in-house developed tool that we called our perception suite, and they were able to run this on their desktop. So again, it was hosted on a server, and they used their web browser. They could use their web browser to run the perception study. For the paper, we had them do it on a clinical workstation so that we could control the lighting and the display more carefully. And so what they were presented here was slice images, not volume images, just slices, and they had to click where they thought they saw the lesion. So this is what we call a detection study. An alternative method that we played with is what's called forced choice. So there you give them 2 or 3 images, and you say which of these images have a lesion in them. And there are trade-offs to how you do your perception studies. Nothing is perfect, but you know, as we're getting into this, we're toying with these paradigms. And then, as I mentioned earlier, another study is where you ask them kind of a more vague question. You know, do you deem this lesion to be brighter than a reference region, or something like that? So there's many different perception studies that can be done. And I've been learning that it's like a field of itself that, you know, it's a minefield. It's no matter what you do, it can be criticized. Why didn't you do it this way? Why didn't you do it that way? And that's why we're working with collaborating the psychology department as to how to design and defend our methods. So what did we do with our perception study? So observers had to point out where they see the lesion on the screen. And then if they were close to it, if they were within a centimeter of the lesion, we said, yeah, okay, you found it. And if they were further away or they didn't answer within, I believe it was 20 seconds, then we deemed it that they weren't able to perceive the lesion. And so you see here a series of figures where lesion size is on the x-axis and contrast with a background is on the y-axis. These are 7 different observers and the performance of the cohort. Clearly, they were able to detect large and bright lesions, but they struggled with small lesions and dim lesions or low contrast lesions, as expected. What we've been working on is developing a psychophysical model that describes the response. So imagine that we fit a curve to these figures and we're able to say, create some sort of equation, parameterized equation of the ability to detect these lesions. And what we're wondering is whether these parameters can be used as a benchmark to gauge the performance of the observers under different conditions or between observers. And so these are what these models look like after we fitted them to the individual observers and to the cohort. So it seems like a combination of these parameters may be useful, but it's still too early on to say for sure. We're planning our first perception study in various cohorts for this summer. So how do we use all this? Like I showed this, sorry, the animation wasn't supposed to be here. This is the scope of the research. So it's in image reconstruction, image display, and observer interpretation that I'm looking to use synthetic lesions to tease out improvements for detecting lesions, both with human observers and with AI. So a lot of the research we're going to be doing is going to be either comparison studies or benchmark studies. One thing that already has been done, but there's always room to in this domain, is to compare image reconstruction methods. So, you know, like, is Q-clear reconstruction, which is offered by GE, superior to OSEM for detecting lesions? That's an obvious kind of application. Display technologies. So this I'm really excited to get going on. It's been really delayed, mostly because of COVID. There's a group in Ottawa that is developing virtual reality for medical applications. And we asked the question of, you know, in that environment, are you better or worse at detecting these lesions? And so we want to have the same users repeat interpretations in the different environments and see how they do, but also inform the development of the virtual reality platform if necessary to improve perception of these lesions. So collaborators are Dan LaRussa and Justin Sutherland, who have launched a startup company called Realize Lab. Really interesting stuff. If you're curious, I encourage you to have a look there. We envision a series of small, easy, very quick studies in which we look at the way we display images and say, you know, is one way superior to another? Fused displays versus side-by-side, PET and CT, different color maps, reading strategies. You know, if you have checklists, if you know the patient history, do you run into issues of satisfaction of search, where once the physician sees what they're looking for, do they stop looking and they don't see other? So there's many opportunities there, and this is intended as a tool to really enable these researchers by non-technical experts, so I foresee fellows and residents training in our department doing these studies almost independently of me. This summer, we're going to be doing our first real perception study, and the question we want to see is that, can we determine difference in skills amongst readers? So if we bring in somebody like a medical student versus a resident versus a fellow versus an experienced nuclear medicine physician, do they perform differently in detecting these lesions? And if so, can we fit these psychophysical models that I spoke about and define some sort of parameter that can be used to benchmark their performance? We're wondering if this could be a way to maybe grade their performance as they go through a training program, to tell them, okay, like now you're operating a third grade level, and in order to graduate from the program, we expect you to be at a grade 5 level. Is that a way for it to kind of for trainees to gauge their performance for detecting lesions over time? Everybody's doing artificial intelligence these days, it seems. We're no different. And so a particular application we'll be looking at very soon is we're going to be looking at creating realistic lesions. So we want to use AI in order to distinguish real lesions from artificial lesions, and that if it cannot do that, that'll be evidence that they look realistic. And we could expand that to using generative adversarial neural networks as a way to define what these lesions look like in the first place. We want to train AI to detect lesions. So for that, we need data, and this could be a way to generate data. But again, it's a more compelling, a more convincing way to do this is if in advance we demonstrate that these lesions can be made to be realistic, right? Because we don't want to train an AI just to detect synthetic lesions. We want to train the AI to detect real lesions. And then finally, and this is, I think, where we could have the most impact with synthetic lesions, is can we use it to characterize AI performance? So you see a lot of work on, well, we trained AI and it's really good at detecting lesions, but those lesions are typically, the ground truth is human observers. So that means that by definition, these lesions are observable, they're often obvious lesions. And so what we want to do is to use synthetic lesions to generate lesions that are barely perceptible, and then be able to also measure how well AI is able to detect these faint lesions, and really be able to score if it's better than humans or worse than humans at detecting these faint lesions. So what's next? Well, some of the work that is going to happen right away is we want to transition to using the new Duetto toolbox from GE that I mentioned. We're really looking to put this in the hands of others. So we've done a lot of development, but now it's time to solicit feedback from other users. Is it useful at all? If not, what is required to make it useful? And we're really happy to be engaged in other people's research. It's much funner than doing the research yourself. As I mentioned, we're going to be looking at creating more realistic simulations. So, not just spheres for tumors. There's still the question of whether we should be reconstructing, simulating the lesions using Monte Carlo and list mode. I suspect that it's not that critical, but if a very keen student comes along and wants to try that out, I'll be more than happy to support them. I wrote CT simulations, but I think what I meant here was creating lesions in CT. So we do that by pixel substitution, which is a very primitive way of doing it. If there's a need and a will, we'll be looking at doing that in a more realistic manner. And then, of course, it would be really nice to take this toolbox and wrap it around some other vendors' tools so that we can support non-GE data that's not just off of GE scanners. And finally, with all that, we'd be able to distribute the tools more broadly, so outside of just the GE research community. We'll be, as we generate lesion databases, then we plan to publish those so that other people can use it without requiring the toolbox at all. And then, of course, we're looking for other ideas and contributions from partners. And so I'll leave it here with a thank you and my contact information. And I'll be happy to take any questions and comments.
Thank you very much, Rand. That was awesome. I mean, so many prospects for your application. Very cool ideas. Very, very exciting. So in the remaining time, do we have any questions or comments or thoughts?
Yes, hi Rand. This is Carlos. Thanks for the talk. It was great. I did take some notes. Let me see exactly. I wanted to ask a couple of things. Okay, I think I want to understand a little bit better how is that you create the lesion in the sense of, I mean, how do you deal with the noise? This is just for FDG images. Would, for example, apply for a PSMA scan? I don't know if you can comment a little bit about that. Yeah,
so I mean, we developed this, of course, in the context of FDG primarily, right? I mean, that's 95% of what we do. And frankly, at the time, we didn't even have PSMA data. Today, we have PSMA data that we could work on. I don't see a fundamental difference between them, except for maybe, as you mentioned, noise levels in different regions. And that's part of the reason why we built in the functionality where you can specify reference regions, so that you can have a relatively large reference region that is, if it's uniform, like a liver, we always assume that the uniform is liver, the liver is uniform, then you can define a large region of interest for sampling that reference region that is relatively immune to noise. But then, of course, when you synthesize a small lesion, noise will be present. There's nothing that we can do about that. It's going to be there. On the upside, to defend that is that, well, noise is a real phenomenon, right? Like we don't that from the onset we wanted realistic images. We didn't want something that looked synthetic, and noise is part of that. We do know, though, however, that if we specify large lesions, on average, their activity is accurate. So regionally, it's accurate, but due to noise, it may not be exactly precise in very small lesions.
Okay, and then but this lesion gets inserted directly into like the reconstructed image, or are you inserting this lesion into the sinogram?
Oh, no. The lesion gets inserted into the sinogram.
Okay, so the lesion gets inserted into the sinogram, but you still are not dealing with like the list file, for example. So for example, if I want to take a list mode acquisition and then I want to do retrospective reconstructions of different durations, I would first have to generate a sinogram for each different duration and then insert the lesion, right?
That's correct. And again, I'm happy to revisit that. We actually started off with list mode. And the reason we didn't pursue it ultimately with GE is that we were operating before the Duetto toolbox came out, and there were just real big practical limitations, right? So for example, you had to replay the list mode on the console. You couldn't replay the list mode on the PC at the time. They didn't have an unlister. GE does data compression on the console. So within like 45 minutes, the data gets compressed. You had to uncompress it on the console. So we were just like, it was too difficult. With the Duetto toolbox, my impression is that that's been resolved. And so happy to revisit that.
Okay, yeah, so we're still having some issues with the Duetto toolbox regarding that. We're trying to run it in Compute Canada, and yeah, it's giving us trouble. Which was also something that I want to follow up. Have you, for example, tried this toolbox in Compute Canada? Because I think it would be a good place to put it. Maybe we can share like I don't know, in the future, like an instance in Compute Canada. We can play doing recons working together. I don't know, just wanted to bring that up.
That's a really cool idea, Carlo. I haven't thought of that before, but if you have experience, I don't have any experience with Compute Canada as of yet, but I think that you're right. Like sharing on a platform like that, and especially if there's the ability to give access to other people so that they don't have to maintain it, they can just come and use it. That's a really nice idea.
Yeah, we can look into that, Ryan, if you want. But
yeah,
as we go forward.
So you've run MATLAB applications on Compute Canada?
Yes, and we're actually trying to now. We have the Duetto toolbox, for example, right now in Compute Canada, and I think it works when we don't have to enlist. We're having issues when we're trying to enlist and do a recon for different time durations, but yeah, we have Duetto in Compute Canada at this point. So
okay. Great. So, I mean, if you're looking to collaborate, then it seems mutually beneficial.
So Ran, a couple of quick comments. We had one of our researchers' undergrad thesis, Kush is his name, and he was being mentored by Ivan, a research programmer, inserting lesions on top of images, not in a fancy and more accurate way that you're doing, but just pure, insertion in the images, showing that can help, detection tasks, for example. And that's one comment. And the other comment, or I guess more of a question. So I look forward to perhaps thinking about using your software to do a similar thing. And the second comment or question is, if we want to look at heterogeneity of tumors and how we are able to quantify that, we might have to do like very fine heterogeneity scale. So is this possible where the original true tumor would be very, very fine, and we would be and we would be investigating, at that very, very fine scale when you're doing a forward projection, and then inserting it and then reconstructing to see how fine of a heterogeneity we're able to measure.
Yeah. So I hope I'm not misspeaking because it's been a while. But my recollection is that we define our lesions on an arbitrary selected matrix, right? So I think we chose like 512 by 512,
That's a good word.
which is just because it was plenty for what we're trying to do.
Yeah.
But if I understand correctly, you want to do it on a finer.
No, I think 512 by 512 is definitely better than what the default is for many, right? Like 256 or 128. So that's definitely good to hear that. But possibly, I've seen finer too. And I suppose you're saying maybe that's a possibility also.
I think it is. Except full disclosure, I'm answering that with 95% confidence.
No,
yeah. So I can get back to you on that.
Yeah. Thank you very much. In the interest of time, it's 3 o'clock. Does anyone have a quick question before we wrap up? All right, seems not. So I'm sure this has been, excellent, and it opens up new horizons of research. I'm sure we will be in touch with you, and we're already thinking about, exciting research directions that can possibly benefit from this. So thank you very much, Rand, for accepting our invitation, and thanks everyone for attending.
Thank you. It's a great privilege, and I very much look forward to collaborating more.
Thank you.